Okay, so let's get started with the first session. Today we're happy to have Xingang Chen from Harvard, and he's going to tell us about alternatives to inflation as cosmological particle scanners.
Thank you very much. First, I would like to thank Guy and Enrico for the very thoughtful organization of this online conference. I think it sets a very good example for a successful virtual workshop. Today, I'm going to talk about alternatives to inflation and in the context of extended cosmological collider program. In order to touch this topic, let me start with two research directions that has been done by us and by many other people that leads to the investigation of this subject. So the first of them, as many of us has discussed, it's not moving, huh? Okay, good. There's some delay. Um, the first subject is the quasi-single field inflation and cosmological collider physics. The motivation of this study is to study the high energy physics probed by inflation. Just as in particle physics, one of the most important objects, information we would like to know is the particle contents of the early universe in this context. So as we know, even if we think about a single field inflations, realistically, what we have in mind is not really a single field, but a landscape of field space with a lot of other particles around. So when we build inflation models, it is a well-known eta problem saying that there are a lot of other massive fields which has around mass of order m square is around h square, h being Hubble parameter, and we need to tune at least one of them to be much lighter. And then that field is the inflaton field that drives the inflation, and we left with many others of order h and higher. So those fields may not, at least in a case where we ignore the sharp features, are not important classically, but they may be important quantum mechanically, and which enable us to see them through the study of correlation functions. So the question is, what are the observational signatures for all those particles around during inflation? Through many studies of researchers, it has been known that it turns out that the mass and the spin spectrum of those particles are encoded in various soft limits of non-Gaussian entities mediated by those massive fields. For example, if we look at the bispectrum three-point correlation functions and take squeeze limit, the bispectrum is proportional to the power of ratio of wave number of the long wavelength modes to short wavelength modes. The power of this ratio encodes the information of the mass, mu right here, depends on whether the mass is takes a low value, this power law become a scaling behavior, or when the mass become higher, this dependence become oscillatory. There is angular dependence with the angle between the long wavelength modes and short wavelength modes. The index S of this Legendre polynomial encodes the spin of the interactions. And this whole amplitude is, of course, proportional to various couplings between massive fields and the inflaton, or more generally, the field which sources the density fluctuations. But it also suppressed by a Boltzmann factor if the mass is higher than of order h. Okay, though there are a lot of applications and extensions of this study that have been used to study various aspects, just as those topics we're interested in particle physics. For example, it has been studied, the standard model spectrum in this context, in inflation background, has been studied in various cases with different symmetry breaking patterns, and it has been extended to now beyond the standard model physics, including many studies which studies higher spin signatures of higher spin fields and signatures of various beyond standard model particles such as stereo neutrinos and gauge bosons arising in particle physics. It has been used to study higher dimensional gravitational ground unification theory and curvature scenarios, and has been extended to strong coupling regime and the effect of galactic halo, its effect on galactic halo correlations has been studied. So this is just some examples. We have very nice talks on those subjects from E. Mark and Sobek in this session as well. On the second related, please feel free to interrupt if you have questions. The second related topics is what we call the primordial standard clocks. As it will become clear later, the one we studied earlier is actually to be better classified as a classical primordial standard clocks. So this subject study the observational signatures that can distinguish inflation and possible alternative. So what's the motivation of studying alternative to inflation? So to this audience, I will just briefly mention several. Of course, we know inflation is a leading candidate. However, there are also several alternative scenarios that have been proposed. Typically, although the statement depending on personal tastes, the alternative to inflation scenarios typically suffer more theoretical problems, more incomplete than inflation, but the improvements along the way, they are active research activities. Second, I would say that by looking at the toy models of alternative to inflations, they act as a reminder that several key features, key predictions of inflation, for example, the horizon, superhorizon perturbations and scale invariant spectrums, may not be unique to inflation scenario. So there may be some alternatives that needs to be explored and tested. Now, even within the inflation scenarios, there are many predictions and possible observables. So it's important to know which set of them are the predictions that can be used to distinguish inflation from alternative ones, and which predictions actually only distinguish between different models of inflation. In fact, the first set of observables is very few. And the only one familiar example is the tensor mode. So it's always good to have some complementary approach. Okay, so the defining property of a scenario, independent of its model realizations, I would say is very simple, just the scale factor evolution, A as a function of time. The approach of this talk will be very phonological. So we will ignore the detailed realizations of any such scenarios, and we will parameterize all scenarios by a simple power law, T to the P, and where P is arbitrary. In fact, as you can see, just by requiring the quantum fluctuations during the primordial epoch to exit the horizon, this power law can be used to describe most of the alternatives that have been proposed. So basically, by fixing the domain of T given a value of P. For example, inflation, the familiar inflation is the one corresponding to the absolute value of P larger than 1. And this, by requiring quantum fluctuations to exit the horizon, fixes the time to run from 0 to infinity. And if P is of order 1 but positive, we have a order 1 positive but less than 1, we will have a fast contraction scenarios, such as matter contraction. For contraction scenarios, we need a bounce to be connected to Big Bang model. If P is close to 0 but positive, that gives rise to a Ekparasis-like slow contraction scenarios. And similarly, if it's negative but close to 0, it describes a slow expansion scenarios. All those three cases corresponding to t running from -infinity to 0. So the question is, are there any observables that can directly measure A of t? This is the question we ask in that direction. The answer turns out to be yes. As I will explain, it's induced by the clock signals by those massive fields, we call them primordial standard clocks.
Xingang, can I ask a quick question?
Yes, please.
So when they're overlapping, in your previous slide, you showed those values of P. If there is overlap between different scenarios and certain values of P, maybe I'm getting ahead of myself, but do you think you can still distinguish between the specific scenario? Like,
yeah, so generally, generally speaking, the approach that I would describe will be measuring this value P, or generally speaking, if you other parameterizations, some short period of evolution history A of t. But I'm not sure I get your question about overlapping P. So these P's are not overlapping at all. The four scenarios have all distinct locations of P.
Okay, so slow contraction and fast contraction is P is like a order 1, but not very close to 0. Is that
exactly?
I see.
The fast contraction is order 1. For example, for matter contraction, it will be 2/3. A slow contraction has a very small P, a few percent.
Okay. Yeah. All right. That was my question. Thanks.
Sure. Thanks for the questions. Yeah. So for being massive.
Can I ask one question?
Yes, please. Yes, please.
So it seems there is one case missing. Can you go to the previous slide?
Yes.
So you don't have P small, close to 0, but smaller. So why is this case? Is there a reason why this is missing?
Close to 0, but less than 0, but negative?
Sorry, close to 1, like the case of a fast contraction.
Oh, close to 1, yeah.
I think it will close to -1.
Oh, yeah. So
I mean the analog of fast contraction, but with P negative.
Yeah. So this is also, if P is negative, it's also a expansion scenario here. Yeah. So if you're close to -1, it's also a expansion scenarios. It's between slow expansion and inflation, but with epsilon bigger than 1. So epsilon is not much less than 1. It's of order 1. So this is kind of in between. Yeah.
But there is no, in a sense, because the case where so you had the fast contraction, you had it as a separate model, but there's no separate model where, in a sense, you have kind of fast expansion, but not inflation, not inflating.
Yes, I agree. So just showing examples of P's that have been studied in the literature, but the parameterization itself can cover scenarios which may not be proposed in the literature. You're absolutely right.
Okay.
Yeah.
Thanks.
Sure. Thank you. When I say massive fields, I mean the mass of those particles larger than event horizon size of primordial epoch. The value for inflation is the familiar H. So those massive fields exist generically in any realistic models if we UV complete them. And one important properties that we use of is they oscillate in a standard way in any background because they're heavier than the horizon scale. Namely, they oscillate harmonically. So those harmonic oscillations will provide ticks for the time coordinates, as I will explain in more details later, induces patterns of ticks as a function of wave numbers in density perturbations, which we call clock signals. I'll explain more in details how those are calculated and what are the patterns. But to realize the models of classical parameter system
Excuse
clocks.
me?
Yes,
Why do they
please.
have to oscillate? I mean, there is a possibility that they're just stuck at the bottom of their potential, right? It's
Exactly. Exactly. You are going ahead of my talk. Yes, I will. This is a very important point, and I will come back. It actually is the main point of this talk. I'll just give some motivations which related some related past projects. Yes, exactly. You're right. So it doesn't have to oscillate classically. But initially, this is what we thought about. So in order for them to oscillate classically, you need some sharp features to perturb the massive fields from the bottom of potential. So on the right-hand side is a detailed example, a complete example of how this process is realized. You have some sharp feature. Here is some rolling down of tachyonic potential, while the inflaton has two stages of inflation, one being very short, and the second, when they find a flatter directions, last longer. So there's sharp features. It can be this kind of falling behaviors. It can also be sharp turnings or interactions with other fields. But the point is, after that sharp features, the massive field is getting permanently or temporarily displaced from the bottom of the potential and start to oscillate classically. So there are sets of predictions that deviate generated by these two processes, 1 and 2. I will describe very briefly for each of them. So if you have sharp features, typically what you see in density perturbations, such as power spectrum, is a correction that runs sinusoidally as a wave number k. So tau 0 is a constant here. They have very model-dependent envelope and phases, but the sine k oscillation, sinusoidal as a function of k oscillation is generic. And this sinusoidal rounding is a signature of a sharp feature. It's not a signal of massive fields. For example, you can have just single field with a glitch in the potential that will give you this kind of behavior. So it does not record A of t as well. But it's interesting to note this kind of behavior is universal even for non-inflation models. So where you have a sharp feature, you will also induce that basically just because a sharp feature can be approximated as a delta function of features in time. So this is independent of P, but this is also nonetheless an important component of full signals that may be useful for other purposes. For example, by identifying the whole signal is generated by massive field. The second observational consequences is induced by the subsequent oscillations.
Sorry, Xingang, quick question.
Yes,
so you said that you're not recording E of t. So what do you learn by measuring tau naught?
Oh, yeah. So for example, one thing we measure is the location or the time of the sharp feature that excites the subsequent oscillation of massive fields. And also because those the predictions from 1 and 2 process are connected to each other. So if you want to do data analysis, you have to work out them all together. So they are smoothly connected.
So if you measure this tau naught, you should leave an imprint also in non-Gaussianity, because it's a particular time during inflation which something special happens.
Yes, exactly. So I'm using an example of power spectrum corrections, but this oscillation, including the oscillations that we talk about in a part 2 process, will have correlated signals in non-Gaussianities as well.
Okay, thanks.
Yes, thank you. So the signals generated by the process 2 is the most important one. It's generated by the resonance between the inverton field or other scenarios, the curvature fluctuations, and the background oscillations. So I will come to that in more details later. But let me just quickly review the result here. So it will also induce some oscillation behaviors, sinusoidal oscillation behaviors as well, with these parameters all being constant. And the KR is also a constant that marks the starting point of these oscillations, which we call clock signals. The main distinctive features of this oscillation behaviors and the previous one is the argument of the sinusoidal functions is no longer linear in K or K for power spectrum example is the modes K1 plus K2. It has some interesting function behavior with the power of 1 over P. And as we explain, and as you can see clearly here, is how this ticks of these oscillations record A of t, because this function behave dependence on K is simply the inverse function of a scale factor of the background. So this phase pattern is actually a direct measurement of A of t. So here is a full set of predictions. It's only a sketch of predictions for various scenarios that I mentioned. As you see, the green lines are all sinusoidal roundings, universal for all scenarios. And the blue lines are all clock signals that has a distinctive patterns in terms of the phases as a function of a wave number. They are determined by the value P here if using this parameterization. And I'm saying this is a sketch because these two signals will be connected smoothly, and you have to work out in more detailed analysis.
So the place where in wave vector space where you start to see these later oscillations, I mean, that's fixed by sort of, you know, when they start oscillating in the landscape during the inflationary scenario?
Oh, thank you for asking. Yeah, I skipped that details. So the displacement between the child feature and the clock signals are determined by indeed the parameters that you mentioned, the KR, but this physically is determined by the ratio of mass of this clock signal to H. So basically, because this determines how fast the oscillation is. So if M over H is larger, the separation between these two will be larger. The ratio of scales of the starting point of a clock signal to the starting point of sharp feature signal will be larger. Does that explain your question? Answer your question? Yeah, it's determined by a ratio of M to H. Okay, so
can I ask?
Of course.
So is the oscillating model like monodromy, does it somehow fit in this classification?
Yeah, I'll mention this towards the end of the talk, but the short answer is no. There are all kinds of different oscillations, but we are trying to pick standard oscillations that we know the origin. For example, the oscillation of massive field, which is harmonic oscillations in the FRWT. So there will be other kind of any repeated patterns can be used as clocks, but they are non-standard clocks, even if it's periodic, but we have no idea where it come from. For example, the axial monogamy model is, in fact, is the approach is we assume it's inflation, but we're using the perturbations trying to probe the shape of a potential. We don't know a priori this is sourced by whichever fundamental physics underlying that. So it's different, and hopefully there are different observational signatures that can be used to distinguish these oscillations from the oscillations induced by standard clocks.
I guess I want to ask a more mundane question. In terms of the time dependence, isn't it the same harmonic time dependence as what you have for a massive field? If I think of it as the function of the proper time.
Yeah, so if you only care about the oscillation patterns, for example, in inflation, the monodromy inflation, or more generally the resonance models, they are periodic. So you all get this sine log behavior as well, but you don't get all this. And also, if you look at non-Gaussian entities, the correlations between different correlation functions, they would be different. So you don't have this. You will have these oscillations, but this oscillation is not decay if we do not tune the amplitude of the oscillations, the amplitude of the ripples on the potential. Does that answer your question?
Yes, thanks.
Okay.
So Xingang,
yes,
one more question about your plot. So in inflation, if the mass of the clock field is small enough, you get like over-damped behavior, right? Just the tail instead of oscillation.
If you have a mass much bigger than h, in fact, if any oscillations will damp as 1 over a cube in inflation or more generally expansion scenarios. So this signal, all these signals is localized in wave number.
I meant a very light extra field, not very heavy.
Oh, if you have very light fields, it doesn't oscillate. If
right,
it's less than h.
It leaves just some envelope, right? Instead of oscillations.
Yeah, it will leave some non-oscillatory bumps in the power spectrum, perhaps,
right?
Which is not very distinctive, and you have to look into it non-Gaussian entities.
Yeah, my question, maybe I'm getting ahead of myself. But my question is, can you get this type of crossover for all scenarios between having like heavy enough fields leaving oscillations and light enough fields leaving tails?
Yes, I think in principle, you can study the whole parameter space and see how they connected.
I see, and it's a mass bigger or smaller than Hubble, regardless of the scenario. The crossover.
Yeah, there will be crossover regardless of scenarios, but the only thing is they will not be used to record A of t if the mass is low. Yeah, that's the only thing, phenomenological purpose. But for other purposes, it's being studied, for example, in cosmological collider physics, where the mass of the particle is less than h. Instead of oscillatory, you have some scaling behaviors, which is as distinctive as the heavy mass cases.
Right. I was just curious if the same type of signatures repeat themselves for the other scenarios, for different scale factors.
Oh, yes. Yeah, I'll come to that related. I will not answer your question in full, but again, as asked by the question by Mark, this will be the subject of a later part of my talk. Yeah,
right.
I'll come to that. Yeah, I'll at least the topic. So by combining these two approaches, and we of course can see they're all studying mass, but they have different motivations and concentrate on different questions. And it's not difficult to see that it seems that we're exploring soundness of dimensional space of rich projects, which as a whole we may call it high energy physics in density perturbations or some kind of extended cosmological kind of physics. We are interested in, for example, the particle contents of the theories with mass taking different values, lower value and higher value. And in this axis could also be spins of the particle contents or even different gravity theories. On the other hand, we are interested in oscillations that could possibly be excited classically. And in the cosmological collider physics, we are interested in quantum oscillations. And we also, one of the directions interested in only in inflation, but other interested in both inflation and non-inflation, as Guy just mentioned. So the previous two directions are just two corners of this whole parameter space. For example, in quasi-single field inflation cosmological colliders, we are concentrated on inflation, quantum fluctuations, but we care about all mass values. For classical oscillations, in primordial standard clocks, we care about all scenarios, inflation and non-inflation, but we only concentrated on classical ones with large mass values. So just by these realizations, you can easily go around and asking yourself is there any other interesting corner to explore? One we will do in this talk, and there may possibly be others. This is using quantum fluctuations, as Mark just mentioned, as a standard clocks. And in the light of the second that I mentioned, is I will generalize the classical oscillations to quantum oscillations. Or in the light of the first direction that I mentioned, it's in view of the first directions, it's a generalization from inflation to inflation plus non-inflation scenario. Okay. So in order to gain more insights and generalize to more inflation, non-inflation backgrounds, I'll give a dynamical explanations of some properties in the soft limit non-Gauss entities. And we have seen many interesting works and talks in this workshop explaining the soft limit behaviors and the behaviors of correlation functions in terms of symmetry and the kinematic arguments. Here I'll give a complementary dynamical explanations. I think both of them are valuable because they provide different insights. The approach that I will explain can be easily generalized to non-inflation backgrounds. Okay, so first, it's not difficult to understand in order to look for as standard clocks, quantum fluctuations of massive field as standard clocks, we need to look at non-Gauss entities. That's because if you look at correlation functions, very schematically, you find two different dependence on momentum. One is its dependence on scale, you rescale all the momentum. Another is dependence on shape. For power spectrum, scale dependence is only one because you only have one momentum mode. So if you study inflation, scale invariant inflation, that prohibits the oscillatory signals that break the scale invariance. So you don't expect to find them in power spectrum. But for non-Gauss entities, we know besides the scale dependence, there's also a shape dependence, which does not, even if they have oscillatory signals, does not break the scale invariance. So the clock signal, it turns out, is hiding there as a function of a shape of non-Gauss entities. And second, I will describe the condition for the massive field for its quantum fluctuations to be qualified as a standard clock. So this condition is what I call the classical regime. It has two conditions. So the mass of the field has to be larger than the horizon scale that I mentioned previously, which is true for classical case as well, except that this horizon scale can be time dependent. Could be time dependent for non-inflation scenarios. And second, I will be interested in the regime where the mass is larger than the physical wave number, namely the wavelength and the massive field is approximately homogeneous over the compton scale of the curvature field, the field such as infotons, which sources the density fluctuations. So this is because this scale is a scale where the resonance happens. I'll explain why. So under these two conditions, if you look at the mode function for massive field in any scenarios, general background, and you will find the behavior of massive field is very similar to the classical ones in this classical regime. Basically, it oscillates harmonically in FRW time with the frequency determined by the mass. Okay, so to understand more clearly the existence of that classical regime, let's go over different scenarios, comparing inflation and non-inflation scenarios. I will use contraction scenarios as an alternative later as example. So here I'm plotting the evolution of different scales as a function of time. And we know for inflation, the horizon mass scale m is roughly h and slowly dropping, so it's almost a constant. But if we look at the physical wave number of the massive field, it's being stretched by the expansion, eventually exit the horizon. So in most part of the talk, I will assume the mass to be roughly constant. So that's the mass scale of the massive field that we hope to use as a standard clock. As you can see, the two different requirements requires the red line to be larger than the green line and the blue line. So indeed, for inflation, we will find such regime right here, as indicated by the bold red line. So once you have this, the reason that we can use it as a standard clock become more clear, because if you look at the curvature field, so for here it's infraton. If we look at the physical wave number of infraton, if this wave number is larger than that of the massive fields, you always see an intersection between this physical value and the mass. Now, this is the resonance point that I will explain shortly, which is crucial for generating the clock signals. It also explains why the clock signals happens in as a shape dependence in non-Gaussian entities when the two momentum takes a hierarchical value, because you require the k curvature to be larger than the k clock. So there is a squeeze limit. If we look at the contraction scenarios, the behavior is very different. So for contraction scenarios, the bouncing scenarios, the mass scale of a horizon rises as a function of time. And also because the universe is contracting, the physical wave number of any fields, including the massive fields that we're interested in, also increasing. The wave number is decreasing as a function of time. Eventually they cross because the contraction of a horizon is faster than the contraction of the scale factor. So the quantum fluctuations exit the horizon. So this is also why the superhorizon perturbations can be natural in non-inflation scenarios. Now, if you look at the behavior of the evolution of the massive fields, you can have two different possibilities, but each of them has a classical regime. Similarly, once you have this classical regime, you just consider any curvature perturbations that has a wave number larger than massive fields, you will find the intersection between the curvature fields and the value of the masses. Okay, so I mentioned the resonance when these two values coincident. The reasons behind that for it to generate the clock signals is the following. This is the first mechanism. I'll introduce the second mechanism shortly. If you have some oscillations like standard clocks, either classical or quantum, and you also, on the other hand, has fluctuations coming from the curvature field, and those fluctuations for the curvature fluctuations has a very simple behavior when the wave number is subhorizon. Basically, it's also harmonic, but in the conformal time space. The conformal time and the FRW time is related by the scale factor. So when we talk about the correlation functions, we are interested in a convolution between these two factors, because these oscillations will appear as a coupling through the field coupling or background coupling to the correlation function mode functions. So we have this multiplication of two factors with some numbers determined by how many point functions they're interested in. So this integration usually is averaged out because they're oscillating, except at the resonance point where the phase is stationary, which leads to a main contribution to the correlation functions given by a T star and tau star, which is evaluated at the resonance point. So if you express this expression as a function of k, you immediately see that the phase has a k dependence that is the inverse function of a of t and a of tau, which we denote as a t function and tau function. So they are inverse functions of a of t and a of tau. Of course, a of t and a of tau are related by simple relations. So we can see the scale factor gets imprinted. A scale factor as a function of time gets directly imprinted in a phase factor here as a function of k. So that's why I say why the resonance here determines the generation of a signal in the previous slides.
Excuse me.
Yes, please.
So I think you said before that you need to look at non-Gaussianity.
Yes, I'll explain that. Yes. Now.
Yeah, but here you are showing the powers, the 2-point function. Is it did something change and I missed, or?
Yeah. So I go through this probably a little quicker. So, but by correlation functions, you can change that to 3-point correlation functions. That just change 2 to 3 or some other ratios.
Okay, so in the 2-point function, it actually cancels.
Oh, yeah. So actually, this explanation, I'm using 2-point correlation as an example because I have in mind both the classical and the non-Gaussian ones. But I explained this. This is more relevant in the classical case because it's 2-point correlation function. You're right. For quantum ones, I really have to look into non-Gaussian, which I'll come back just in one slide. Yeah. So, but the mathematics, the physics that determines this encoding is exactly the same. It's just by giving this. Because if you have 3-point correlation functions, you will have 3 mode functions here with some couplings. And actually, it's more complicated. With 3 here, I'll explain that in one more slide. Just hold on. Yes, good question. Thank you.
Xingang, can I ask a quick question?
Yes, please.
Could you explain your attitude towards the scale invariance of the adiabatic mode? Because you're writing down just the e to the I k tau, but in a generic model, I won't get scale invariance. So we're just not worrying about that, or what is your attitude?
My attitude is still this is highly model dependent. So scale invariance has something to do with the k dependence in front of these oscillation factors, which typically has a much weaker dependence on the k. It's not dramatically oscillating as this one. So we are looking at some high oscillating components embedded within the scale dependence that you are talking about. So, so of course, when people realize their scenarios models to be viable with observations, they have to make their factors correct. But I'm just talking about any oscillatory corrections that might observe beyond their effort to make the leading order predictions to be compatible with experiments. Does that answer your question?
Sure, thanks.
Yeah. Sorry, it gets frozen. Okay, now I come back to ask my dad to answer my dad's questions about non-Gaussian entities. So as I just showed previously, the quantum fluctuation massive field in the classical regime, they behave very similarly as the classical ones, right? So, and also explain there's a hierarchical scales between the k cloud and the k curvature, as one being a long wavelength modes, another being short wavelength modes. So, so in this classical regime and in this soft limits, and as I'll say, the previous 2-point correlation functions. I didn't, my don't answer your questions, explain as clearly as this graph. But if you look at this graph, the behavior between these two, the interactions between these two modes is very similar to the classical ones that I mentioned earlier in the talks. That is, you have background oscillations, which now is some quantum fluctuations in classical regime, modulating two short wavelength modes. So this is what the non-Gaussian tells us. So now the mathematics is almost identical to the previous slides, except that when you work out the consequences, it tells you the dependence is in the ratio of these two momenta. So you have to go to a hierarchical limit of these two momentum. And also, the explanations, the dynamic explanations I explained earlier can be easily generated to arbitrary scenarios. So because I didn't make any use of inflation scenarios, except to argue that let's first look at non-Gaussianities. But we'll come back to power spectrum for non-inflation models quickly. Okay, so
Xingang, should I recover 3/2 for the envelope up front for inflation, or what is the number for inflation?
Oh, yeah. So this is non-Gaussianity. This is non-Gaussianity. It turns out the envelope here is -1/2 because for inflation, P is infinite. So it's for example, for scale invariant inflation, it's power law with P goes to infinite. So it's -1/2. It decays.
I'm just confused because usually we say it's K1, K long over K short to the 3/2, but
exactly. So I understand. So that intuition is good in classical case because the massive field gets diluted. In fact, in the quantum case, you also see this 3/2 appearing, but I think I didn't have a mathematical answer clearly in my head right now. But I think the fact that you end up with -1/2 has to do with something with when you calculate the correlation functions, some other envelope behavior that come from the curvature modes. So they somehow cancel them or enhance, change the behavior of this power law. Yeah.
So do I understand correctly that the power is growing as I make the long modes longer and longer?
Okay, so if I make the long modes, no, if long modes longer, K3 is smaller, so this whole ratio is bigger. So the envelope is decaying, which is
okay.
At least this is consistent
Okay.
with the intuition that the massive field has to be diluted. Yeah.
Okay. Okay. Good.
Yeah. It's just the power is slightly different in this case, and despite a change in the K dependence from the scale dependence to shape dependence, the functional form is still inverse function of A of t. So this oscillation pattern encodes A of t. So here is a full set of a sketch for different scenarios. Very similar to the classical case. The quantum case here has a dependence on the ratio, and we look at non-Gaussianities. Okay, so now come back to the connections that I mentioned previously to different corners of a space, parameter space that we have already studied. And let's go back to the cosmological characteristics that we're familiar with in inflation. And we take the massive field limit, heavier limit. And actually we see this actually encode inflation background. To see this, we just rewrite this power law dependence. Remember, this now is imaginary for heavy mass case. And this is just sine log dependence. And in retrospect, the fact that we get log in cosmological physics is precisely because we have already assumed a expansion in the background. because this is the inverse function of exponential. So the cosmological collider physics is measuring not only the particle spectrums, but at the same time, even we didn't realize, it actually also measuring the scale factor evolution of the inflation background just by staring at the log dependency. I just briefly mentioned the amplitude of those signals, quantum fluctuations. Now the classical oscillations, once you push them, it can go as large as 1, but that's a model building issue. The quantum fluctuation is more general, as Mark previously also mentioned. You just let the particle sit at the bottom and the world fluctuates. But the amplitude is much more subtle because it might be small in general situations, although the signal generally exists in models much more generally than the previous one. So the situation is very similar to a tensor mode. Depends on what kind of couplings you're interested between massive field and the curvature fields. And here I'm using some concrete models of inflation, quasi single field inflation as example. You'll get various range of FML. And the most optimistic one is you couple in the self-interactions among the massive fields. That basically is given by the observation. And also you have to pay a penalty of Boltzmann suppression. Okay, so now after studying the non-Gaussianities.
Xingang, just one more question about non-Gaussianity. Did you look into the power dependence of the collapse limits of the trispectrum?
We didn't. That'll be interesting to look at, but in order to, the reason we concentrate on the soft limit is we want the hierarchy between modes to vary to some extent. So that inevitably will lead to some, at least for the trispectrum, leads to a squeeze limit. The class limit don't.
Well, you can still take the hierarchy between the intermediate particles and the external ones.
Yeah, we haven't looked at them. And you actually can take the folded limit and go to the squeeze limit. That will be exactly the same as this because we didn't specify the angle between the short wavelength modes and the long wavelength modes.
Okay.
Yeah. But you can look at more generally what happens when you vary along around the folded limit. Thanks. Okay, so now we ask what happens in power spectrum because in inflation, in alternative to inflation scenarios, the Lagrangian self does not have a shift symmetry. The scale invariance in density perturbations is caused by construction. So this is especially interesting for alternative scenarios to inflation. But if we look at the power spectrum, we only have one momentum and no hierarchical scales. So it's not on. It should be no resonance. So we have to look at the phase of massive field mode function. So here is a equation of motion for the massive field in a contraction background. And as there are 3 terms, the second term determines the horizon mass scale, and the third is the wave number of massive fields, and the last one is the mass. So these 2 we already mentioned the behavior in the contraction background. But then if we look at the relevance of the K terms, there are regimes when K is small, these K terms never play a role. They're below both scales. But if we make K large enough, specified by this combination, larger than 1, some intermediate period for the massive field, the K term become dominant. And there's a crossover between the M dominant regime and the K dominant regime. So this crossover is important. Eventually, the horizon scale will always dominate, just because all modes exit the horizon. So it turns out that something interesting happens. That's a generation mechanism for clock signal mechanism 2 is if you just look at the massive field without look at its coupling to the background oscillations or quantum oscillations of massive field, there's also a place where the scale factor evolution gets encoded. That's just happens in the phase. If you look at the phase of this mode function between the change between the M-dominated region and the K-dominated region. So in this K-dominated region, you can simply solve these mode functions. And without taking the assumption of specific function behavior of A, you can already see how the inverse function of A enter here. But if you make the template, power law template, you can work out much more explicitly. So for the contraction scenarios, early on, this massive field will be dominated by these harmonic oscillations. The mass dominates. And eventually, the horizon dominates, so you have harmonic oscillations in the tower space. So during the transition, the crossover that I mentioned previously, this mode pick up a phase that has a phase dependence on K, inverse being the inverse function of A of t. If you look at the expansion scenarios, the conclusion is very similar, except that now you require K to be small enough, not large enough. And early on, it's K dominated, and later on, it's mass dominated because it's expanding. Similarly, you pick up a phase which contains the clock signal. So once we know that, and then it's easy to go to look at what happens of the impact of this phase on various correlation functions mediated by massive fields. It turns out to be similar for 2-point correlation functions and 3-point correlation functions, but now we are not going to squeeze limit, even if we consider 3-point correlation functions. We look at the limit where all 3 momenta are comparable to each other, but we look at the scale dependence. So let's just concentrate on 2-point correlation functions for simplicity. And we will have correlation functions that are contributed by a massive field, which is a V here. U is curvature field. And when you look at these integrations, and you can notice that for all scenarios in the classical regime and the K-dominated regime, the mode functions are oscillatory. So there's little contributions. So the main contribution for alternative scenarios coming from the horizon dominated regime, when the modes exit the horizon, where the contribution is no longer that oscillatory. But we already know that before this regime, the mode function already pick up a phase here, which is time dependent. And then it's easy to see that if you have this time dependent phase, and if you have both components, the positive frequency and negative frequency components, once you take the conjugate, or an absolute value, once you multiply its value with its complex conjugate, you have some interference terms which can successfully record the phase factor into a sinusoidal function as a function of K. Now this become similar to the K dependence that we are familiar with previously. And the requirement is you need to have 2 components. So I don't know currently if this can be relaxed or it's actually general for alternative scenarios. But this is the results we got so far. And you can see this dependence now is a scale dependence. Okay, to make a comparison between inflation and non-inflation scenarios. Inflation, we're familiar with, only probe a scale around H or below. And so if you have different particles with different masses, the signal of those signals, the signal of those particles will lay on top of each other in a K space. So they're all extended in a K space. That's analogy of collider physics with a fixed energy scale. But if you look at the alternative scenarios, you again look at the tower of actual particles. But as I mentioned previously, the horizon scale of the alternative to inflations grows in time. So it actually scans over a tau of scenarios. And remember, we have a condition where the crossover happens when the wave number of the massive field is either, or the wave number of the curvature field is either large enough or small enough. So that translated into the K dependence of those signals appearing. So for example, for particle 1, which is green line here, you have no signals for smaller K at large scales, but signal only appear at certain K value and start to oscillate. If you have a different mass particles, particle 2, it happens at a different scale. The situation is reversed for expansion scenarios. So you can view the alternative to inflation as a cosmological scanner that scan over the tau of particles and display the signals of each of them as a pulse of signals at different length scale in density perturbation.
Xingang,
yes.
Let me ask a quick question. So there are people in the audience that are more expert than me in this, but there's this trapped inflation scenario where there are bursts of particle productions, and then you can probe maybe 60 times H or something like that.
So that scenario I would categorize as sharp feature scenarios, because without any sharp features, the sharp feature there is interactions, you will not be able to convert the kinetic energy of the infraton into other particles.
So you think that you'll be able to distinguish this? I was wondering if it was degenerates with this scanner scenario that you had in mind.
Certainly, first of all, it's not. You're talking about by distinguishing. We're talking about to distinguish them with several different cases. For example, for this alternative to scenario cases, as I just about to mention here, besides the particle contents that we mentioned, so this kind of signals also carries direct information of AFT, because the oscillatory behavior is a characteristic of that background expansion. And I think it's not true for the inflation scenarios, except for some caveats that we'll mention briefly. And if you are talking about distinguish that scenarios from the quantum standard Cox case I talked about previously, it's even simpler, because the previous case for inflation don't have this kind of oscillations in power spectra. We look at the squeeze limit of the non-Gaussianities. Yeah. So the scenarios I talk about belongs to sharp feature scenarios, where I expect to see some oscillations, combination of oscillations that is a characteristic of sharp feature, and the resonance, basically the ripple on the potential type of signals. Yeah. To address that in detail, we have to compare the predictions, but they are different qualitatively, as I just mentioned.
Okay, thanks.
Yeah, sure. So once this information about AFT is measured, that actually is a nice feature that we can use to falsify competing scenarios in a model independent way, because we are not doing model building in this approach. So last slides, I think I'm running out of time. So, but I will summarize this in the next couple of slides. And some key features that makes the previous mentioning of massive fields being a standard clocks is the following. I just refresh and summarize. So first of all, we require the mass, the value of the mass of this field to be larger than horizon scale. So this requirement makes the oscillation very simple. As long as the mass is approximately constant, it's harmonic oscillations, any time different background. And also at various places that we see where the clock signal are generated during resonance or during the transition between two different regimes, all the quantum fluctuation is in the sub-horizon scale, meaning deep in the horizon scale, irrespective of inflation or non-inflation. So this sub-horizon scale is very important, because it makes this method much more general, because sub-horizon behavior is standard. for the curvature modes or infraton. They are basically just the Minkowski limit behavior. Well, if you want to make, if we were to make use of a superhorizon limit of scalar fields or curvature fields, that will be much more troublesome because the superhorizon modes is very model dependent. They evolve outside the horizon. Assumption we make is the mass of clock is constant. So there will be, it's an interesting topic how such signals, if we have some time-dependent mass, dramatic enough, and how to distinguish them. So that's that we will call a non-standard clocks. Basically, is the upshot is any repeated signals can be used as clocks, and they may confuse part of the signals that we work out to distinguish different scenarios. The example of non-standard clock is for any parallel background, you can engineer oscillations of this form. And the reason this form interesting is the mass scale corresponding to these oscillations will scale the same way as the horizon scale of this background. So it traces the horizon scale. So that explains why if you use these oscillations, you will see an oscillation signal very similar to the inflation, a sine log with some constant. This actually is the motivation behind when we propose the primordial standard clock, the classical one, to look for the standard ones generated by the massive fields and try to work out the predictions associated with that as much as we can to distinguish the oscillation from massive field from the oscillation from some other, from massive field with constant mass from some other oscillations, including the oscillations from massive field with time-dependent mass. So recently, there are some detailed study model building that construct such models. For example, Yi has a nice talk in this session that make use of this coupling of massive field to the curvature modes, which actually is a model building realization of that kind of oscillations, which then give you mimics the sine log behavior. And also there are some works trying to construct the field dependent mass terms for the massive fields. The time dependence come from time dependence of phi. So it turns out once you mimic this sine log behaviors and it's associated with some other changes in other properties of oscillations, such as envelopes that we also mentioned for the inflation case. And also you have to, if you want to mimic all correlation functions, you have to tune each of them. And some of them at some point, you stop being able to tune, and even if you introduce some extra parameters. And also there's a question also answered by, also asked, is about how to distinguish the standard clocks with any other periodic or non-periodic features in the potentials. So they are in principle also can be used for clocks, but we don't know the nature of clocks, so it's not a standard clocks. So they can be distinguished from massive field by, for example, sharp feature signals and non-cos entities and detailed dependence, etc. Okay, so I think I'm running out of time, so I will not talk too much about data comparison, and just briefly mention that on the topic that there's a large set of relevant data analysis relevant to this talk. If I concentrate on the scale-dependent ones, as we are interested in the scale-dependent glitches, namely the residue in the CMB data. So there are various interesting glitches. Some are well studied, some are less well studied. But currently, they are all statistically marginal, and they can be fit by many scenarios. And for example, we recently did some fit with alternative scenarios that we just mentioned. And the future prospects is to use various other experiments like CMB polarizations, large scale structures. They will improve the constraints, especially large structures will be able to improve order of magnitude, 1 order of magnitude more precise. And more futuristic is the 21 centimeter experiments. That will provide much more modes and much more tighter constraints. But this is challenging because the potential is great, but those experiments are very challenging. So I think I will stop here. So if you have a question about the observational aspects that I skipped at the end, please let me know during the private session or discussion session. Thank you very much for your attention.
Thanks, Xingang. So we had a lot of questions during the talk. Maybe we have time if there's one more, and then we'll move on to the discussion.
Sure.
Is there anyone with a pressing question?
Can I ask a question?
Yeah,
yes.
go for it.
Yeah, I have a question about non-Gaussianity in alternatives. So what is the typical amplitudes for non-Gaussianity in alternatives? So you provided amplitudes in inflation, but what is for alternatives?
Yes, that's a great question. So the reason I only present for inflation scenario is basically there are inflation is much better studied than alternative inflations. A short answer to your question is no. I don't have any specific numbers in mind or ranges in mind for alternatives in inflation. So the reason is I took a model independent approach phenomenologically. So I don't even look at specific scenarios of alternative inflation. All that matters to me is A of t as a background. So it will be nice for people who build the concrete signals of alternative inflations to work out some of the examples more explicitly and figure out what's the range or what's the upper bound of various amplitude, or whether they actually are already excluded by experiment, etc. Yeah, thank you.
Okay, thank you.
May I comment on Toshi's question? So since he was asking alternative to inflation, there are so many models. So the non-Gaussianity, size of non-Gaussianity very different, could be very different at least. But let me give you an example. For example, in the matter contraction scenario, the non-Gaussianity can be naturally of order 1. Actually, they are talking about a problem. The non-Gaussianity is too large for massless modes. And you can easily consider that to generalize that to mass of order Hubble parameter, which doesn't change the order of magnitude of non-Gaussianity very much. So that will be also for the 1. I guess that would also happen for ecliptic scenario, but I didn't check through the calculation. Yeah, but it's model dependent.
Yeah,
thanks.
At least you can see one distinction is here. As long as you're at the right scale, you don't have Boltzmann suppression. Because the heavy field and the light field in alternative inflation is relative, depending on time. So initially heavy fields, after you wait for a while, become relatively light fields.
Okay.
Okay. I